Greetings everybody, and today we're going to be taking a look at a couple of examples of vector spaces. So in the previous video I introduced the axioms of vector spaces. So those are the 8 axioms along with the 2 closure axioms as well. And any set with 2 operations plus and scalar multiplication that satisfies those axioms, we call them vector spaces. So let's get straight into it. Let's take a look at the first example, which is the set of all 2 by 2 matrices over the real numbers. Now, how are matrices vector spaces? Well, first of all, this guy is definitely a set, and we need to define 2 operations, which is a plus. We're going to define this to be matrix addition, and we're going to define this dot over here to be matrix scalar multiplication. And you can check that all the axioms for matrix addition hold, namely it's commutative, it's associative, there's the neutral element, which is just the zero matrix, and there's the inverse element, which is the matrices with all the entries negative. So the plus operation satisfies all those axioms. Same with the scalar multiplication as well, you can check that as well. So what we can say is that M equipped with this plus and a scalar multiplication, this guy's a vector space. Next example, this one's a little bit more abstract, but we're going to define F from S to R, where S is any set over here, to be the set of all functions which take you from S into the real numbers. So FSR, it's a set of all these functions. So it's a bit weird, and it's not like a set of all these arrows that we're used to. No, it's not a set of vectors at all, it's a set of functions. And in fact, the set of functions is also a vector space. And we can show that by defining 2 operations plus and scalar multiplication, which we'll do down here very soon. And now to distinguish this plus from the plus on the real numbers, which might get a bit confusing, I'm going to make this a circle. So this is the plus on the vector space, not the plus on the real numbers, the plus on the vector space that we're going to be defining. So how does this operation over here work? Well, it's going to take 2 elements from FSR, so FSR cross with FSR. What is it going to do? It's going to spit out another element in FSR. And how are we going to define this thing over here? What we're going to do is we're going to take a pair of 2 functions, f and g, in this Cartesian product over here. And what we're going to do is we're going to send this to a new element in FSR, and we're going to call that f circle plus g. So simply adding these 2 functions together, whatever that means. Now, what even is f circle plus g? Well, we know this, we want it to be in the set of functions from some set S to the real number. And usually in this topic, whenever we're dealing with these maps over here, we're sending maps to other maps. These new maps that we get, it's always best understood when they act on something. So what is this guy over here? It's a map from S to R. So we can say for all S in this set S, how do we define this guy? We can define f circle plus g. This is a map, so you can think about this as a function which acts on this S over here. So this is a function from S to R. It must act on an element in S. And how do we define such a guy? Well, we can define this to be equal to f of S plus g of S. So notice over here I turned the circle plus into normal plus. Why is that? Well, it's because f of S, that's a real number. This function already acts on an element in S, gives us a real number. We also have another real number over here. This is the addition on real numbers, so we don't need that circle plus, because over here we're adding 2 functions, not 2 real numbers, we're adding 2 functions. So this is how we define circle addition. Now, we also need some kinds of analogous operation to scalar multiplication. We call that a circle dot in this case, and I've got 2 colon over here. But how does this guy act? Well, we need a field of scalars. What field of scalars should we pick? Well, there's a couple to pick, but let's go for the real numbers. Now, I'll explain why real numbers is a good option over here, not something like the complex numbers. So we're going to take the real numbers, so this is going to be a vector space over the real numbers. We're going to take a real number along with an element of FSR, and this is going to map to, you guessed it, FSR. Now, how is this going to work over here? Well, let's take a real number lambda along with a function f in our set FSR. This guy is going to be mapped to lambda, similar to this over here. We're going to have circle dot F. Now this is an element of FSR, which means this guy eats an element in S and spits out an element in R. In order to understand this well enough, we need it to act on, well, an element in S. So this guy over here, this is a function. What I wrote down is a function. It must act on an element S. So again, for all S in S, we define this to be lambda times f of s. And again, notice I changed the circle times back into normal times, because this is the multiplication on the real numbers, because f of s, that's already a real number. Now back to the reason why we want our field of scalars to be R, not C, for instance. If this was complex over here, then we would have complex coefficient. This lambda would be a complex number, which means this map, it actually maps not to the real numbers. It's because so far this is the real numbers over here. It wouldn't map to a real number anymore. It would actually map it to a complex number, because the lambda might be complex. Now this is a bit of a problem, because our set's FSR, it doesn't close under scalar multiplication. We might get a function that's in a totally different set. So that's why we want our field of scalars to be R, so that it actually closes. You could also choose the rational numbers as well. That definitely closes, but we can just go for R. Now, we have operations defined in our set FSR. We also need to check that these operations satisfies those 8 axioms, and those are quite easy to check, because what you can do is notice that R is a vector space, and what you can do is you can inherit the vector space structure of R onto all these maps over here, because they all map to the real numbers. So first of all, we can check that this guy, F circle plus G, is commutative. Why is it commutative? Or it's because it doesn't matter which way you add these two functions over here, it's the same thing. Why is that the case? Well, because f of s and g of s, those are real numbers. It's also an element in the vector space R. And you can do that with all the axioms as well. You can also check that it's associative. Some other things I want to point out is the neutral element. So what is the neutral element? 0 in the set FSR. Well, 0, if it's an element in FSR, it's definitely going to be a map from S to R. So to map from S to R, how does this guy work? Well, what it's going to do is it's going to send every element S in S to 0. That's all it's going to do. And you can check that 0 is in fact the neutral element, because if you have F plus 0, circle plus 0 actually, there should be an element in your vector space FSR. You let this act on an S, and you use the definition of this plus that we have over here. What do? We just let each of the functions act on the element S. So this would be f of s, normal plus, because this turns into addition over real numbers, 0, but you act on s. But notice 0 acting on anything is just 0. So this would give you f of s. So in fact, this is the neutral elements over here. You also have the inverse element, which we call minus f. If this guy is in your set FSR, then it's definitely going to be a map from S to R. This maps from S to R. How does it work over here? Well, we can define S to map to our normal f without the negative of s, but then what we do is we multiply the whole thing by a -1. And we can check that this is indeed the neutral element by using the axiom. If you have f circle plus minus f over here, this guy is an element of your FSR, so it must act on an element S, and we use again the definition of this circle plus right over here. This is going to be f of s. This circle plus turns into a normal plus of what do we have? You have minus f acting on s, but we already know what minus f of some s is. It's simply going to be, well, just the negative of that. So this becomes a minus f of s, and this is equal to 0. And yeah, you can interpret this as just 0 of s. So in fact, f circle plus minus f, that gives you back the 0 over here. So that's for the addition. You can go through the scalar multiplication axioms as well and check those. Those are pretty straightforward. So what do we conclude from this? We conclude that FSR equipped with plus or circle plus and circle dot, this guy is a vector space. Now sometimes you might drop these circles and just replace it with normal plus and normal times. The only reason why I put circles over here was just to distinguish it from the real numbers. But if you just understand that, well, these are just two operations in the set, there's no real reason to put circles. You can just leave it as plus and multiplication, as long as you know what you're operating on. So next, and probably the last example for this video, let's take a look at the set of P and R, where this guy over here is defined to be the set of all polynomials of degree at most n over the real numbers. So what does this look like as a set? Well, it's going to be the set of all these polynomials, which I'll write as the sum from I goes to 0 to n of ai x to the I, where ai are from the real numbers. So far what do we have? P and R. This guy is a set. It's just the set of all these polynomials over here with a degree at most n. Now we can actually turn this into a vector space over here by defining appropriate operations for our plus and scalar multiplication. So we can take a look at the plus. How does this work? It's going to take two elements, so you can say this is the Cartesian product, and it's going to send it to P and R, which is another polynomial over the real numbers. Well, we know each of the polynomials in the set looks like this big sum over here, so we can say this is sum going from I equals 0 to n of ai xi, the circle plus, and we use a circle plus over here because we're adding two polynomials together. I going from 0 to n of bi xi. How is this guy going to be defined? Well, we define it as another polynomial, but we simply add the coefficients component-wise, you can say. So this is I going from 0 to n of ai plus bi xi. So this is how you can define this circle plus on your sets of P and R. And notice this plus over here, that's a plus on real numbers because we're adding together two scalars. You can define scalar multiplication as well, which isn't too hard to do. You can define this circle dot over here. And now this is a polynomial over the real numbers. So in fact, you want your field of scalars to also be the real numbers. You don't want it to be complex, otherwise you'll have complex polynomials. So you take an R, you take the Cartesian product with, again, this set P and R, and you expect to get out, well, P and R. And how can we define this? We can define a lambda circle times into a polynomial, which is a sum from I equals 0 all the way up to n of ai xi. You can define this guy to be equal to the sum from I goes from 0 to n. Now for all these ai's over here, you're going to multiply by this lambda. So kind of like when you have the polynomial, you distribute that scalar in front into all the coefficients. That's essentially what you do. Okay, you replace it with normal multiplication of ai, because these are two real numbers, and this is times xi over here. So you can define addition and scalar multiplication on polynomials, and it's very clear that it doesn't matter which way you add two polynomials. It's commutative, it's also associative. You also have the neutral element, which is just the zero polynomial, literally just this zero function over here. And you also got the inverse element, which, well, you just take the polynomial, multiply each term by negative, and all the scalar multiplication axioms are pretty easy to show as well. So what do we conclude from all this? We conclude that P and R equipped with this addition and scalar multiplication, this guy is also a vector space. And again, you don't need to put these circles on this plus and scalar multiplication. They're just there to distinguish from the operations on the real numbers. So if you want, you can get rid of these. Get rid of these if you don't like the circles, but because I have it in the definition everywhere, I'll just leave it there. So these are some examples of vector spaces. Why are they vector spaces? Well, because they're sets with additional operations which satisfy all the vector space axioms, which means they're vector spaces. So notice these don't necessarily have to be arrows in space with a bunch of coordinates and whatnot. They can be any abstract mathematical objects that you put inside of the set over here, and you define these two operations on them, and they obey a bunch of axioms, and what we call them vector spaces. So those are some examples of vector spaces. Hopefully you enjoyed this, and I'll see everyone next time.